You put your hand on both of these, and this one over here feels cold, right? And this one feels the same temperature as your hand, basically. All right. Now, I'm just going to put a little ring on each of these for a reason that'll become obvious in a minute. Here's the weird part. You may need to stand up if you can't see this. I'll put an ice cube on both of these. Doesn't really matter which one. Put an ice cube on both of those. This is the cold one. Okay, if you can't see in the back, you can stand up. This is the cold one. That's the one that felt cold, and this is the one that did not. It felt like room temperature. And that one is almost completely melted already. Didn't switch them. You can come up and feel them again if you want to. It's not, was David Blaine. This is not like Mind Freak. This is just science.
I'm going to a David Blaine show soon.
Is it really David? Is that his name? I just made that up, really. That was pretty good. I only see it from commercials. I've never seen him. But, okay. So isn't that weird? Now, but if you think about it, it actually does make sense. If this feels cold, what's it doing? It's taking heat away from your hand, right? Yeah, it's sucking heat out of your hand. That's why when you touch something metal in the wintertime, right? It feels really cold and takes the heat away from your hand. Because some things, like this, is a good insulator. This stuff is, I believe, I ordered this from a kit. I'm pretty sure this is the stuff they use on the tiles for the space shuttle. For re-entry, it has to be able to dissipate a lot of heat. So it's a great insulator. It's not a very good conductor of heat. You wouldn't want to have it made out of metal because that would conduct the heat right through it. This ice cube hasn't done anything. It's not even. This was completely melted already. All right, and all has to do with something called specific heat. And we're going to get to that at the end of the period today. But you can see what basically some things heat up and cool down faster than others. That's all that I'm trying to point out here, and I'll tell you why and how it's going to affect us in our calculations in a little bit. All right. So this is all part of thermodynamics. All right. And like I told you before, I don't have notes to give you anymore. So if you don't have paper for today, I'll give you a piece of paper, but you are going to have to start bringing your own. Anybody need any paper today? Anybody need any? Okay, we're going to be back to taking regular notes like we did in Chem 1, not filled in, because there aren't as many drawings and pictures and formulas as there were in organic. All right. Okay. Chapter 15, thermodynamics. All right. Oh, never did the board. Hold on. All right. Thermodynamics, Roman numeral 1, thermodynamics. What is it? Well, you probably could figure it out from the word thermodynamics. Energy changes. Dynamic means changing, and thermo usually means something to do with energy or heat. Right? So it's a study of energy changes associated with physical and chemical processes. Now, in Chem 1, we actually did do a tiny little bit on thermodynamics. Some of the stuff I'm going to see here again, you're going to have seen in the past. And for the most part, most of the labs we do, and we have a lot of labs in this chapter, actually, I think we have 3 of them. A lot of the labs we do in this chapter are going to be associated more with the physical than the chemical changes, because we're going to calculate the specific heat of a metal. All right, that's pretty much a physical change. All right, we're going to be doing just mixing hot and cold water and predicting the next temperature, like what the new temperature would be. If I take a certain amount of hot water, a certain amount of cold water, given the calculations the formula is going to give you, you can actually predict. Say I gave you 100 grams of water at 80 degrees Celsius and 50 grams of water at 30 degrees Celsius, and I mix them together. You can predict what the new temperature would be. All right, and I can even do it if it's not water. If I add water and something else, that is a different specific heat. All right, so most of the calculations, most of the labs you're going to do are going to be with physical until the second half of the chapter, and then we're going to be doing more of the chemical stuff. The point of thermodynamics, believe it or not, is to determine whether a reaction can occur or not. It determines the spontaneity of a reaction. Believe it or not, I make up stuff all the time. I think you probably figured that out. I'm doing my notes. All right, but just because I put an equation on the board doesn't mean it actually works. Okay? I make up things all the time just to make a point. The fact is, some reactions are spontaneous and others are not. And I can determine, just because I wrote two elements, this plus this yields this, doesn't mean it actually happens. All right? You have to look up the thermodynamics of the equations, and it will determine whether that reaction is spontaneous or not. All right? And that's what we're going to be able to do in this first chapter. By the way, just like organic was an obvious theme, for 5 chapters, we did something different about organic chemistry, carbon compounds. For the next 4 chapters, we will have a theme. The first theme is whether the reaction occurs or not. That's the whole chapter. The goal of this entire chapter is to do that. It's going to take me a long time. This chapter is going to be about 3 weeks long. It's going to take me that long just to be able to tell you whether the reaction occurs. Just because it does occur doesn't mean we want to do it anyway. There's 2 other things we want to talk about and 3 other chapters we're going to go over. But this is the first one, whether the reaction occurs or not. That's the point of thermodynamics. Once you know that, you know whether you should at least try it. Because after that, we're going to have to figure out how fast it occurs and something else called the equilibrium of it. But you don't know what that is yet. Okay, now, in this first day, we're going to do, and then I'm going to give you pretty much, I don't know, the whole period, the second half of the period, but quite a bit of time in the next half to do some of the calculations. I got 1 as a bonus, actually 2 that are kind of like bonus questions, but 1's really only the bonus, but 1's harder. On some calculations, I want to give you some new terms. These are the terms we're going to be using all chapter. And some of this, again, you saw very briefly in Chem 1, but I want to go over them again. Because these are terms you have to understand, and we often get, a lot of these are going to be things we either don't know or get confused. Energy is the first one. If we're talking about energy change, you should know what energy is, right? Okay. Potential energy. Now, I did this last year, I know, when we talked about the difference between potential versus what? Kinetic, okay? Remember I did the little dragon and all that stuff? Remember that? Yeah. Okay, I mean, I don't want to have to go through that whole thing again. We did that once before. And basically, potential energy is, you know, if I'm on my castle and I've got bowling balls, my example was bowling balls and bombs, both of them the same mass. They have the same potential energy as far as Schrader's concerned, because that's physics, right? They both weigh the same. They're both at the same height. That's the energy of position. Kinetic energy is the energy of motion. So you drop them and they fall, okay? But there's a different kind of potential energy and kinetic energy when it comes to chemistry. It's not just how high the chemicals are, it's what's in the bonds. We could drink water all day long, we're not getting any energy from it. But if we eat sugar, we're getting energy from it because there's more energy in the bonds of sugar than there is in water, what we could get from our, when we break it down. Okay? So it's the energy a body possesses by virtue of its position. That's physics. How high is it? We don't care about that in here. Or its composition, what it's made of. Certainly dynamite has more potential energy in its chemical bonds, in its molecular composition, than a bowling ball. So if I throw down the same mass at the dragon who's attacking my castle of dynamite and a bowling ball, one's going to hurt him more. And it's not the bowling ball. Okay? So that's potential energy. You guys remember that I did all that yet last year. Kinetic energy, of course, is the energy a body possesses by virtue of its motion or while transferring heat. So in chemistry, we don't care as much about whether the beaker's falling off the table in motion. What we care about is how hot it gets. In every lab we do this chapter, we're going to have our thermometers out. We're going to be using them, all right, and calculating temperature changes, because that will give us the clue as to how much energy was transferred when I carried out this reaction, whether it got hot or cold. We all know that some things get cold. Endothermic reactions, right? They get cold. That means they're absorbing heat and not releasing it. Okay. So there's potential versus kinetic energy. That's the first term we want to talk about. All right? Or the first terms, I should say. Now there's heat versus temperature. You may remember this from Chem 1. You don't have to draw this yet. Wait till I finish talking about it first. All right, what I have here are 2 containers. Okay, remember this from last year? I have container A and container B. Now, You don't have to draw because I have some notes to write down here too as well. I'll put them underneath it after we're done. Let's say container A is at no, use green there. 90 degrees Celsius. And container B is filled up with water at 90 degrees Celsius. What can I say about their temperatures? They're the same. They're both filled up with water, I just said. Both containers are filled up with water at 90 degrees Celsius. What can I say about their heat? B has more heat than A, or A has more heat than B? B has more heat than A. I always get that wrong. It's amazing. We did this exact same picture, exact same thing in Chem 1, only I gave you the notes first in Chem 1, and then I did this. Here I'm doing this first. And yet, about half a year, about half and half from what I heard yelled out A or B. All right? And you have to think about what heat means. I didn't give you the definition first this time. That was just the phone making a noise. B has more stuff there at 90 degrees. Let me ask you this. We all know law of conservation of matter and energy. Can't create or destroy matter. Can't create or destroy energy. To heat this guy up, if this were all filled with water, I put him on a stove. This were all filled with water, I put him on a stove, I heat him 90 degrees. Who's going to take longer to heat up? Everybody knows that. Everybody gets that right. You had to put more heat into him, didn't you? Then it's got to be there. It's got more stuff. Heat has to do with the quantity of energy in an object. Temperature is just the intensity of that. If I were in a darkened room and couldn't see how big these were, and I put my finger in this one, and I put my finger in that one, they both feel the same. Their intensity of heat is the same. However, if I were to come back to that room, leave it, come back, which one would have cooled off faster? A, because there's not as much there. It's like a small cup of tea versus a big pot of tea. All right? Small cup is going to cool off pretty quickly. It's going to take a lot longer to heat up a big pot of water. All right, so let's give you a little bit of notes because it's a good thing I did this because, again, about half of you kind of had it backwards. Temperature is the intensity of heat in a system. And what's it measured in? What do we measure temperature in?
Celsius.
What Celsius? Degrees. Degrees Celsius. Or what else? You're going to find you use this? Kelvin, yeah. Okay. It's measured in degrees Celsius, Fahrenheit, or Kelvin. Now, I said before in Chem 1, I didn't make you calculate between Fahrenheit and Celsius. All right, in Chem 1. Here I am going to, because you will probably see it somewhere along the line in your high school, or college, I should say, career. You're probably going to have to convert between Celsius and Fahrenheit and Kelvin. We did a lot of Celsius to Kelvin temperature changes, right? What were they? What did that involve? 273 plus Celsius gives you the Kelvin temperature, right? But I'm going to have to actually give you the Fahrenheit formula this time. It is something you have to kind of memorize and use. It's a pain. It's not that hard, obviously, but still, it is something that you will have to do. Has anybody ever done it in a math class anywhere? Probably have a couple of math classes. All right. There's your Celsius temperature. You can look at it either way. Celsius equals Kelvin minus 273, or Kelvin equals Celsius plus 273. That's the way we usually see it, because we're usually converting into Kelvin to get our temperatures in order to use them in the gas law equations. Remember, you had to have them in Kelvin. Oh, and by the way, that's a dash. It's not minus Celsius. But there's the one you're going to have to be able to do. And by the way, this is something we haven't done all year. Math. In organic, you guys, everybody complains because we complain about everything. But we complain about organic, all right? But the fact is, you had very little homework in organic, and you had virtually no math in organic, all right? Well, that's gone. You're going to have a lot more math, and what's going to get our feet wet here a little bit, why don't you try rearranging right now, because I'm going to do it for you in a second. Rearrange that equation and solve for F, because that's what you'll have to do both ways. On the homework tonight, and well, actually it won't be homework, you'll probably get it done in class, but on the test for sure. Rearrange that guy, and then I'll do it for you. See if you get Fahrenheit correctly rearranged.
Might be lying. I think he might be lying.
Let's see how you did here. Because remember, the good part about this, and let's be honest, the good part about there's good and bad to both of these. Organic didn't have a whole lot of homework, but it was harder. All right, it didn't have a whole lot of math, but the tests were harder to do well on. This chapter will have homework. You actually will have. I mean, today because you have a double, you probably won't have very much homework, but you are going to have homework. You are going to have more math problems to do. They are going to take longer. But the good news is you won't really have to study as much for these tests because these tests are going to have much fewer objective questions like vocabulary or stuff like that. All right, let's see how you did here. What would you do first to this guy? Well, I would multiply both sides by 9/5, right? Okay, so I get 9/5 degrees Celsius equals Fahrenheit minus 32, right? And now what do you want to do? Add 32. Okay, I'm just doing this for a good reason. Obviously, believe it or not, that shows you the two major concepts in any rearranging of algebraic equations. What you do to one side, you do to the other, both in math and in multiplication and in addition, right? It's very simple. So I will add 32 onto this side and add 32 onto that side, and I will get 9/5 degrees Celsius plus 32 equals Fahrenheit. Is that what you got? Right? Or Fahrenheit equals 9/5 degrees Celsius plus 32. And there's a degree sign there too. All right. Well, you're going to have to use both of those. You don't have to memorize both, obviously. You just have to know one, and then be able to solve for the other one. All right. So there's temperature. Here's heat. Heat is the quantity of energy in a body, and that requires you to take into account how big the body is, how much of it you have there. Hence my little example a minute ago with the two containers. The larger one at the same temperature is going to have more heat. Okay? How do we measure heat, by the way? What units do we use to measure heat? You should know this.
Joules.
Joules, exactly. Or in chemistry, we more likely use what? Same thing you use for your food.
Calories.
Mm-hmm. In physics, you use joules, and you're probably more used to using that from everybody in here having physics, I believe, or having it right now, one or the other. But in chemistry, we actually use calories more. And by the way, the calories for your food, remember I used this before, that's the same kind of calorie. It's just 1,000 times bigger. When you see a candy bar has 150 calories, okay? It's the same calorie I'm going to talk about here, only times 1,000. It's like a kilocalorie, all right? Because here's all a calorie is doing. If I take that candy bar and I were to burn it, however much energy it would give me, all right, that's the same amount of energy I'm going to get when I eat it. And how do they measure that energy? Well, we're going to do that, actually, in a couple of labs. We're going to be we're actually using specific heat. All right, but here's what basically it means. All right, the calorie is this big, long definition here. And I'll explain it to you. Just copy it down first because you won't listen to me. Where you get this from, and I believe Mrs. Spencer used to do, and I don't know if they still do anymore, used to have people come in from that Science in Motion lab. You ever guys have this, like a van that came in and did labs for biology? Maybe when you guys were in freshman year.
Right.
Mrs. Anybody have Spencer? You would have been the last class that could have, I think, as a freshman.
I don't think you're wrong.
Yeah, that means probably not. Well, anyway, they would have. You could actually. You know what else? Who does it? I think Bond over in the middle school.
Well, he's here. He's in the
I know, but when you guys were there, he was in the middle school, right? You ever burn like a peanut or a cheese doodle, and measure how hot the water got?
I don't remember.
You ever do that?
It's been so long.
I think he did that. I think you can burn pretty much anything. Now, peanut burns very well. And if you measure how hot the water, you burn it and see, measure how hot the water gets, you can calculate how much energy is given off when that peanut's burning. Well, basically, that's what a calorie is. It's the quantity of heat needed to raise the temperature of 1 gram of water 1 Celsius degree. Notice that's not much. 1 gram of water is like a half an eyedropper full. And 1 Celsius degree is not very much, obviously, right? To raise the temperature 1 Celsius degree, 1 gram of water, all right, that's what a calorie is. That's the definition of a calorie, okay? And I can relate calories to joules, and you'll have to do this for many calculations. Calories are related to joules by that little conversion factor. 1 calorie equals 4.184 joules. And it is a conversion factor you're going to be using the same way we've done conversion factors in the past. Units in the bottom, units in the top. All that stuff that we haven't used half of this year because of organic. We've done almost no math. You're going to be doing conversion factors. You're going to be doing algebraic manipulation. And you're going to be doing some math that we haven't done before. All right? Like, for example, by the end of this chapter, there'll be, not this chapter, by the end of this unit of 3 chapters or 4 chapters, you'll be doing stuff like FOIL. Remember FOIL? The quadratic equations? Remember that? You'll be doing that. You'll be doing a little bit of calculus, but not much. You're not going to make you do derivations. I'm going to show you how you would do it, but I'm not going to make you do it. A little bit of calculus. So you're going to see a lot of this stuff. Even exponents and logs you're going to use too. But again, this chapter is actually the easiest. It's mostly just algebra. And the algebra in this chapter, believe it or not, can get hairy. All right, so you have to be meticulous, especially having not done it for a while. All right, so that's what heat is. Heat is the quantity of energy in the body. It's measured in calories. That's what a calorie is. I'm going to relate all this together in a minute, okay? When we talk about specific heat, which brings us back to my demo. I did it in the beginning, so you can all. I don't want to make it, get up in the middle of the notes here. But specific heat is what I illustrated by this guy right here. This little demo we just did. Look, the one that's on that insulated block, it's still ice. It's melted a little bit, but the other one's been melted for the last, 20 minutes. What is specific heat? Well, it's completely illustrated by these things here. It's how easy or hard it is to heat something up. It's how well something conducts energy. It's the quantity of heat. Now, here's a technical definition. It's the amount of heat it takes to raise the temperature of 1 gram of anything 1 Celsius degree. Obviously, it doesn't take much energy to heat up that plate that felt cold. It conducted energy very well. It was made of metal. I believe aluminum. Whereas the other thing is an insulator. And it doesn't conduct heat very well. It's very difficult to heat that up. Or cool it down. Or change its temperature in any way. Do you notice a similarity between that and my definition of calorie a minute ago? It's almost the same thing with the exception of, for calories, it was about water. Okay? It involved water. How much energy it takes. That's our standard. That's where we get the calorie from. How much energy it takes. In other words, the specific heat of water must be what? 1. 1 calorie. It takes 1 calorie. Now, does that mean everything's going to have a specific heat? Is water easy? What do you think? Is water going to be easy or hard to heat up compared to, say, a metal? Be a lot harder to heat up than a metal. Okay? And that's why we use water as a coolant in our cars, in the power plant up the road, because it's so hard to heat up. It cools things. It absorbs a lot of energy from our engine while we're driving, so the car doesn't overheat. It absorbs a lot of that energy from the power plant, that nuclear reaction that's going on there, that heat is generated, turns into steam, takes a lot of energy to do that. So we use water as a coolant. All right, we use it as a coolant because it's so hard to heat up. Matter of fact, I'm going to have you guys open up to your books. I know I haven't given you the books yet. I'm going to have to probably pause it. Open up your books and look at the chart on the back of your in Appendix K, I think. Let me see. Anyway, it's different for every substance, and I will show you those values. You can look them up in a minute. Appendix E, I believe it is. So I'm going to pause this right here, and I have you guys go back and grab a book. You have. There's the other thing about this.